During World War II, the Allies built a weapon so secret they gave it a fake name: variable time. Two perfectly boring words chosen specifically so enemy intelligence officers would read them, yawn, and move on. The real name was the proximity fuse, and even that was classified, because the mere concept of an artillery shell that could sense a target and decide when to explode was considered too dangerous to say out loud. If you've heard of it, you heard about the engineering. The tiny radar set stuffed inside a shell, the Doppler effect. You didn't hear about who actually built it, because that part was buried for decades. The proximity fuse has been ranked alongside radar and the atomic bomb as one of the three most decisive technologies of the Second World War. But while the Manhattan Project got bookshelves full of biographies and Hollywood films, the proximity fuse stayed strangely faceless. A weapon everyone agrees was transformative, and almost nobody can tell you who created it. So let's fix that. This story starts not in America, but in Britain, in September 1940, with a chemist carrying a battered black metal deed box across the Atlantic Ocean. His name was Sir Henry Tizard. He was a former rector of Imperial College London, chairman of the Committee for the Scientific Survey of Air Defence, and the leader of what might be one of the most consequential diplomatic missions of the 20th century. And the mission was, at its core, an act of desperation disguised as generosity. Here's the situation. Britain is getting bombed. Factories are burning. The entire scientific establishment is consumed by the immediate demands of radar, of cryptography, of simply not losing the war in the next 6 months. British scientists had been thinking about proximity fuses since 1931 and 1932, when two researchers at the Royal Arsenal in Woolwich, W.A.S. Butement and P.E. Pollard, first sketched out the concept of a tiny radio transmitter embedded in an anti-aircraft shell that would detonate when it sensed reflected energy bouncing off a nearby aircraft. Brilliant idea, completely impossible with 1930s electronics. Too big, too fragile. The concept got shelved, revived in 1936, picked up again with fresh urgency in 1939. And every time, the same wall. Britain could imagine the weapon. It couldn't build it. Not while the Luftwaffe was overhead. So Tizard's mission made a calculation that Churchill himself was initially uneasy about. Could the Americans keep secrets? Would sharing Britain's technological crown jewels simply enrich a future rival? But survival beat pride. Britain needed America's factories, its laboratories, its sheer industrial mass. And the price of admission was everything in that black box. And what was in the box was staggering. Tizard brought a team that included John Cockcroft, the Cambridge physicist who'd split the atom in 1932, and Edward Taffy Bowen, a Welsh radar pioneer. They carried details on jet engine design, submarine detection advances, anti-aircraft gunnery data, and the centerpiece, a resonant cavity magnetron about the size of a hockey puck that would revolutionize radar. But they also brought the proximity fuse research, Butement and Pollard's original concept. The subsequent work at the Air Defence Experimental Establishment at Christchurch. Everything Britain knew about making a shell that could think. The Americans received this intelligence on September 19, 1940, and it landed on the desk of a man who was, at that moment, the most powerful scientist in the country. Vannevar Bush, engineer, organizer, relentless bureaucratic operator, had already convinced President Roosevelt to establish the National Defense Research Committee months earlier. The NDRC existed to mobilize American science for a war everyone could see coming. When the proximity fuse concept arrived, amplified by the British data and parallel research already underway at the US Naval Research Laboratory, Bush didn't hesitate. He knew who he wanted. Merle Anthony Tuve, 40 years old, physicist at the Carnegie Institution of Washington's Department of Terrestrial Magnetism, and a very specific kind of brilliant. Tuve had grown up in Canton, South Dakota, building crystal radio sets with his childhood friend Ernest Lawrence, the same Lawrence who'd go on to build the cyclotron and win the Nobel Prize. Where Lawrence became famous for building ever larger machines, Tuve became expert at extracting results from whatever was at hand. At the Carnegie Institution, he'd pioneered bouncing radio pulses off the ionosphere to measure its height, work that was, quietly, the conceptual ancestor of radar itself. He understood radio waves, he understood electronics, and he understood something Bush needed even more than technical knowledge: how to lead brilliant people toward practical results under insane pressure. Bush assigned Tuve to lead Section T of the NDRC in August 1940. The T stood for Tuve's own initial. His mission? Build a working proximity fuse, which meant building a radar set small enough to fit inside the nose of a 5-inch artillery shell, and rugged enough to survive being fired from a gun at forces of 20,000 Gs. That number deserves a moment. 20,000 times the force of gravity. Instantaneous. Every vacuum tube, every solder joint, every wire inside that fuse had to endure a mechanical shock that would pulverize virtually any electronic device in existence. The vacuum tubes of 1940 were glass-enclosed, thumb-sized, and absolutely not designed for this. Most electronics engineers didn't consider it a challenge. They considered it absurd. Tuve didn't care what they considered it. He staffed Section T with physicists, engineers, and mathematicians pulled from universities across the country. Among them was a quiet, intense young physicist named James Van Allen, fresh off his doctorate at the University of Iowa. 2 decades later, Van Allen would discover the radiation belts encircling the Earth that carry his name today. In 1940, he was just one of dozens of talented scientists who showed up at Tuve's lab and got told what they could deliver mattered, not their credentials. Tuve was reportedly blunt to the point of abrasion about this. Colleagues described a man with enormous energy and zero patience for academic preciousness. He inspired fierce loyalty anyway, because everyone knew he'd never ask them to do something he wouldn't do himself. By early 1942, the program had outgrown the Carnegie Institution, and that's when Johns Hopkins University entered the story in a way that would define the entire effort. The Applied Physics Laboratory, APL, was formally established in March 1942, initially housed in a converted used car dealership in Silver Spring, Maryland. A used car dealership. That's where one of the most important weapons programs of the war was headquartered. Tuve became APL's first director, and the laboratory exploded in size, eventually employing some 700 scientists and engineers. The atmosphere inside APL was intense, improvisational, and deliberately anti-hierarchical. Tuve organized teams around problems, not departments. He didn't care about organizational charts. He cared about the fuse working. The breakthroughs came piece by piece. The miniature vacuum tubes were the most critical, ruggedized with new internal structures, developed in direct collaboration with manufacturers like Sylvania Electric Products, and tested until they could survive the violence of a gun barrel, not in 1 out of 10 firings, but in 9 out of 10 or better. The power source was another nightmare. You couldn't have live batteries sitting in ammunition dumps for months. The solution was a wet cell battery, with the electrolyte sealed inside a glass ampule. When the shell fired, the 20,000 G acceleration shattered the ampule, flooded the battery cells, and brought the fuse to life in milliseconds. Elegant, brutal, extremely difficult to manufacture reliably. But here's the thing nobody mentions when they talk about the proximity fuse. The fuse was only half the system. This is the part that transforms the story from clever shell to something much bigger and much stranger. Because what the Allies actually built by 1943 and 1944 was a semi-automated anti-aircraft weapons system, decades before the word automation entered common use. It worked like a chain. First, the SCR-584 radar, a microwave set developed by the MIT Radiation Laboratory, detected and tracked incoming aircraft with continuous precision, feeding data on position, speed, and altitude. That data flowed directly into the second link, the fire control predictor. These were analog mechanical computers, not electronic computers. Assemblies of gears, cams, differential analyzers, and servo motors that took the radar's tracking data and mechanically performed the calculus required to figure out where the target would be by the time the shell arrived. Not where the plane was, where it would be. The M9 gun director, developed by Bell Telephone Laboratories, was the American masterpiece of this technology. Bell Labs, the same institution that would later give the world the transistor, was, during the war, building analog computers for gunnery. The M9 took continuous electrical inputs from the SCR-584, computed lead angles, ballistic corrections, and fuse settings in real time, and transmitted firing solutions directly to the gun mounts. The guns moved themselves. The Navy's Mark 37 Fire Control Director did the same thing aboard warships, integrating radar data to direct 5-inch batteries. And then the proximity fuse, screwed into the nose of each shell, ensured the round didn't need to actually hit the aircraft. It just needed to get close. When all three technologies operated together, something eerie happened. The gun crews stopped aiming. They were loading. The radar tracked the target. The computer calculated the solution. The guns swiveled on their own. Once these systems were fully implemented, the crews didn't even look at the targets. They watched the loading mechanisms and kept ammunition flowing while the integrated system handled everything else. Men feeding shells into weapons that were firing at things they themselves could barely see, trusting entirely in an invisible chain of radar, computation, and radio detonation. The statistics are blunt. Before the integrated system, it could take thousands of conventional anti-aircraft rounds to bring down a single aircraft. After full integration, the rounds per kill dropped dramatically. The most vivid proof came during the defence of London against V1 flying bombs in the summer of 1944. When the buzz bombs first appeared in June, batteries using conventional fuses were destroying roughly 24% of incoming V1s. When units equipped with the full system, SCR-584 radar, M9 predictors, VT fused shells, deployed along the coast, the kill rate climbed past 79% within weeks. That's not an improvement, that's a transformation. But all of this, the science, the system, the stunning effectiveness, would have meant nothing without something even harder to achieve. And this is where the story reaches its climax. Because you can't win a war with a $732 fuse. That was the cost of each proximity fuse during the early development stage at APL. $732 per shell. For a device you fire once and it's gone. If the Allies were going to deploy the VT fuse on any meaningful scale, and meaningful meant millions of rounds, Someone had to figure out how to mass-produce miniature vacuum tubes, wet cell batteries, radio transmitters, and precision electronics inside an artillery shell, at volumes and costs that would have seemed delusional to anyone who understood what was inside those shells. Commander William Sterling "Deke" Parsons, a Navy officer with a deep technical background and a gift for navigating military bureaucracy, became the essential bridge between APL's scientists and the industrial base. Parsons could discuss circuit design with TUVI's engineers, then walk into an admiral's office and explain in operational terms why this fuse would change naval warfare. He fought to keep the program funded, to accelerate testing, and to push the fuse toward the fleet as fast as humanly possible. Parsons would later be selected as the weaponeer aboard the Enola Gay, one of the very few individuals who played pivotal roles in two of the war's three most important weapons programs. But in 1942, his war was the proximity fuse. The manufacturing scale-up that followed was, frankly, insane. The government contracted Johns Hopkins APL to oversee the research, then farmed out production to industrial firms across the country. Crosley Corporation, Sylvania Electric Products. Others, the network eventually included multiple manufacturers producing components and complete fuses on staggered assembly lines. The challenge wasn't just volume. Each fuse contained miniature vacuum tubes that had to survive 20,000 Gs. Wet cell batteries with glass ampules calibrated to shatter at exactly the right moment. Radio circuits that had to transmit and receive with consistency across hundreds of thousands of units. Every single fuse had to work. A dud wasn't just a wasted round, it was a pilot alive who shouldn't be. And they did it. Production ramped to 250,000 proximity fuses per week. Let that number settle. 250,000 per week. That's one fuse every 2.4 seconds, around the clock, 7 days a week. And the cost? It fell from $732 per unit to $18, 97.5%. That drop represents thousands of small innovations, process improvements, manufacturing shortcuts, quality control systems, material substitutions, made by engineers and factory workers whose names never appeared in any history book. They couldn't talk about what they were building. Wartime secrecy meant the people on the production lines often didn't know what the finished product actually did. The fuse went to war. On January 5, 1943, the light cruiser USS Helena, operating in the waters near Guadalcanal, fired the first VT-fused shells in combat against incoming Japanese aircraft. The results were immediate and dramatic. In the Pacific, the fuse became critical to defending against kamikaze attacks, where a maneuvering aircraft diving straight at your ship was precisely the scenario where a proximity fuse's ability to detonate close enough could mean the difference between a near miss and a catastrophe. But the fuse had a restriction. It could only be used over water. The standing order was absolute. The VT fuse was never to be fired over land where the enemy could recover an unexploded round, reverse engineer the electronics, and either build their own or develop countermeasures. For 2 years, this policy held. Naval use only. Nothing over territory the Germans or Japanese could search. Then came December 1944, the Battle of the Bulge. Germany's last major offensive in the West smashed through Allied lines in the Ardennes, and the situation was desperate enough that the restriction was lifted. For the first time, VT-fused artillery shells were used over land, not as anti-aircraft rounds, but as airburst weapons against exposed German infantry. The shells sensed the ground itself and detonated not on impact, but at a height of roughly 20 to 70 feet above the surface, producing an airburst that showered everything below with shrapnel. General Patton himself described the proximity fuse as one of the most remarkable munitions developments in the war. And then, when it was over, silence. The classification stamps stayed on. The workers who'd built 250,000 fuses a week went home and couldn't tell anyone what they'd made. The scientists at Johns Hopkins APL moved on to other projects. James Van Allen went back to studying the upper atmosphere, eventually discovering the radiation belts that made him famous. And almost nobody connected that achievement to the young physicist who'd helped build a radar set small enough to fit inside an artillery shell. Deke Parsons became known for Hiroshima, not for the fuse program that consumed years of his life before he ever boarded the Enola Gay. Merle Tuvey returned to pure research at the Carnegie Institution and rarely spoke publicly about the war. The story calcified around the engineering marvel, the clever little shell, rather than the relay race of human beings who made it real. British scientists who conceived the idea and then handed their nation's secrets to strangers because they had no other choice. A physicist from South Dakota who turned a converted used car dealership into one of the most productive weapons laboratories in history. A Navy commander who spoke both the language of engineers and the language of admirals. Factory workers who assembled precision electronics at a pace of 1 every 2.4 seconds without knowing what they were building. And a network of manufacturers who crashed the cost of a miniature radar set by 97.5%. The proximity fuse wasn't one genius invention. It was proof of what happens when scientists, engineers, and factory workers across two nations sprint toward the same finish line with everything on the line. A relay race across an ocean, where the baton was a concept and the finish line was 250,000 tiny radar sets rolling off assembly lines every single week. These are the people nobody talks about. Now you know their names. If you want more stories like this one, the hidden chapters behind the things everyone thinks they already know, subscribe. There's always another layer.